Now we want to turn our attention to non-right angle triangles. Everything we've done so far has dealt with ratios in right angle triangles, but obviously we know that we're not always going to have problems that we're going to face with right angle triangles. So what happens when we have non-right angle triangles? So what we're going to use are two rules. First one we're using is the SIne rule. So obviously it's SIne rule because we're going to use the SIne ratio in a lot of these. Now I haven't provided the proof, but you can find the proof on the net or in your text. So if you want the proof of why this rule exists, then it's there. But I'm not going to go through it in this video. So the idea of a SIne rule, if we have our triangle labelled like this, so we've got a side A, and typically our triangles are labelled this way, with the capital letters on the vertices and the small letters on the sides, opposite the sides with the vertices with that same letter. So the little A is opposite the big A, and so on for the for B and C. So the rule is that if we take it in any triangle, any side over sine of the opposite angle will be in the same ratio. So A on sine A, B on sine B, C on sine C. And that happens in any triangle. So no matter what the triangle is, the value of the side over sine of the opposite angle, all the sides will have the same ratio. Now, really what it comes down to, there's two rules, SIne rule and cosine rule. We have to have a particular set of data to use the SIne rule. And the two situations where we use this are where we have two sides and one not included angle. What do we mean by that? Well, if we've got B and C, then if we have the angle A, then we can't use the SIne rule to find A. Okay, that's going to be the cosine rule. But if we've got B and C and we've got either angle B or C, then we're going to be able to use the SIne rule because we were able to put that into play. Or if we get two angles and one of the sides, we're in business. Because once we get two angles, we've got all three angles. So two angles gives us all three, and then if we've got one of the other sides, we'll be able to find one of the other sides to work with. So that's where we're going to use this rule. And if we don't have these situations, then it's the cosine rule that comes into play. So let's have a look at using this rule. We've got a triangle here. We've got x opposite sine of 33 degrees and 52 opposite 79. So we've got two angles and one of the sides. So the SIne rule is going to be able to work here. So we set it up as we do with the ratio. So the side x over sine of 33, the side of 52 over sine of 79. So notice we're putting the sides opposite in that ratio. So, and then what we want to do is solve an equation. We've got an equation with one unknown because we can calculate sine 33 and sine 79. So we put our unknown by itself by multiplying by sine of 33. So we get our ratio, we get our relationship here to x, and then we put that all in the calculator, calculate it out, and we get 28.85, which is one of the answers up there. So again, for question 2, we've got x opposite 85, 12.9 opposite 41. So we set up our ratio. X on sine of 85, 12.9 on sine of 41. So multiply through by sine of 85 and then put it in the calculator and gives us 18.22. Now, when we do these ones, we should think about whether that answer is reasonable as well. So just in case we do make a mistake with our calculator work or multiplying or dividing, 18.2, how reasonable is that answer? Well, remember in any triangle that when we look at any triangle, the largest side's opposite the largest angle, the smallest side's opposite the smallest angle. So if 12.9 is opposite 41 degrees, then we should be expecting that x would be greater than 85 degrees, greater than 12.9 because 85 is greater than 41. So 18.22 comes out as greater than 12.9, which sounds reasonable. So as soon as we did this, looked at these answers, we should have been able to say, well, get rid of B straight away. Can't be B because that would give us a side that's smaller than 85. So keep that in mind as you go through and do these questions. So let's have a look at the next one. This time we're finding an angle. Now, we said before that we had the side on the angle, but we can write our sine rule this way. Sine A on A equals sine B on B equals sine C on C. We were able to do that because we can just take the reciprocal of each side, each ratio, and turn them upside down. They'd still be equal, as long as we do it to all of them. So this side where we're finding an angle, it's a little bit easier to write it this way. And notice 4 is opposite theta, and 5 is opposite 78. So we write sine of theta on 4. So that's sine of that angle on the 4. Sine equals sine of 78 on the 5. So we're able to write it that way. You can write it the other way and then keep manipulating. But this is a little bit easier. We're saving ourselves a little bit of time and effort because we've got the sine theta and we don't have to do too much because when it's in the denominator. So again, multiply through by 4, we get 4 sine 78 on 5. So sine of theta must be equal to that angle. So we take the inverse sine, or on your calculator, shift sine of the 0.7825. Keep that number, don't round it off. Just keep the whole calculator answer in your calculator. And then coming down to degrees and minutes, we put it into our calculator and we get 51 degrees and 30 minutes. So that's how we start to find an angle. Try and do it that way. It doesn't really matter if you don't. If you keep it the other way and put 4 on sine theta and 5 on sine 78 and manipulate it from there, that'll still work. This time we've got theta opposite 52, and we've got 122 degrees and 15 minutes opposite 78. So we're able to set that up. Sine of theta on 52, sine of 122 degrees 15 minutes over 78, and then sine of theta would be equal to that expression. Put in your calculator and then take the inverse sine. We get 34 degrees 19 minutes. This time sine theta is opposite 12.5. The 43 degrees 22 is opposite 18.3. So again, set up your ratio, multiply through to get sine theta by itself, and then once we've got a decimal, once we calculate it, inverse sine of that gives us that angle. So keep doing that process. Set it out first, then manipulate it. Try not to do what some people have been doing and just trying to skip steps and then get errors. So set it up properly to start off with. Show that application of the SIne rule to start off with. This one is a little bit tricky. So let's look carefully at this one. We've got to work out theta, which is opposite 89, and 24 is opposite 13. So we set up our ratio. Now the trick with this one, if we go back into this one where we saw sine of 122 degrees 15 minutes. Now from what we were doing with the angles in the 4 quadrants, we know that will give us sine of 122 degrees 15 minutes will give us a positive answer. But there's also an angle in the first quadrant that would give me the same answer, because sine in the second quadrant is positive, so it's an obtuse angle. So that's going to be the same idea here. We could technically take anything when we look at these angles here. We could technically take any angle in the first or second quadrant. We didn't take the angle in the second quadrant for this one. So if you put sine of 0.51685 into the calculator, you get 31 degrees 7 minutes, but you could also get an obtuse angle. It wouldn't be an obtuse angle in this case because it's opposite 12.5 and it can't be larger than 43 degrees 22 minutes. Sorry, it can't be larger than 83. If I got the obtuse angle, then that angle would be opposite the smaller side. So it can't happen in this case. But we're not sure here. We're not sure, even though our diagram looks like it's an obtuse angle there, it could be an obtuse angle here because it's 89 millimeters against 24 there. So it's that's the smaller side to this one. So when we do this calculation, as we've done before, we get the 56 degrees and 32 minutes. But also, if it could be 123 degrees 28 minutes, because it could be that angle in the second quadrant. So that could be the obtuse angle, or that could be the obtuse angle. Just because it's not drawn to scale as such, doesn't mean we can't take those two angles. So that's where D is our answer for this question. And you could go back and do that. Put sine of theta on 123 degrees 28 minutes, and sine of theta equals 56 degrees 32 minutes. Put them back into both those, and they both satisfy that expression. So that they both work, and from our diagram they could both work. So be wary of that situation. It doesn't happen very often, but again, what it's about is understanding what our diagram looks like, what our given problem looks like, and whether we could get two answers for theta, depending on whether it's the side opposite is large enough for that to happen. So here's one where it's a bit more involved. I'm going to use a bearings type problem here to use the SIne rule. So if we look at setting up our diagram according to what happens here. So Gabriel hikes 8.2 kilometers at a bearing of 036. So there's the 36 degrees. So hikes at 063. So, and hikes 8.2 kilometers that way. She then travels the direction of 152. So notice we've gone 152 around here. So 90 degrees plus 62 is 152. And it doesn't say how far she travels, but she travels far enough in that direction. And then, for that to happen, her bearing there is going to be from a to her starting point of 287. So the bearing around to there is 287. So she travels far enough this way, so the bearing from her to her starting point. So if you look back, she looks back to her starting point. She's at an angle. They'll be at an angle of 287 on that compass. So that's what our diagram looks like. So notice we've been able to write that as 36 because they're alternate angles. That's 28 because 28 and 62. So we were able to get an angle there. It's not 90 degrees, so we're going to have to deal with either the sine or cosine rule. So calculating the distance she travels in the second stage of the hike. So we want to calculate this side. So have we got enough information? Well, that's 64 degrees when we add those two together. And because we know that that was 287, so it goes 17 degrees there, we're able to work out that that would be 17 degrees there. And this one would be 36 from 90, which gives us 54 degrees there in that part, which allows us to get 71 degrees in that angle. Now, because that's 71, that's 64, that leaves us with 45 as our third angle there, because they must add up to 180 degrees. So there's the trick in that one, is to try to get those angles. That we've only really got one angle one side, but we've got enough data to get two angles, because we know that's 287, so that would be 17, and so it allows us to get those angles there. We've got the 8.2, that leads us to get the x that we want to find on the first in part B, then allows us to find y in part C. So we look at our calculations. X on 71, sine of 71 equals 8.2 on sine of 45. So we do our calculations, and for B she's travelled 10.96 kilometres. In C, we said we should have to go back y. Then we put y in over the sine of 64, the 8.2 on sine of 45. So we're able to calculate that she has to travel 10.42 kilometres to go back. And then the last part, well, it's not really part of the trigonometry, but if she averaged speed of 2.9 kilometres an hour, how long would the trip take? So we take our three distances. It relies on us getting our distances from B and C, because we had the 8.2 kilometres in the question. So there's our three distances. She's travelled that distance completely, divided by 2.9, because that's how fast she travels. Remember, our distance our time equals distance over speed. So remember those relationships, and that gives us 10.2 hours, or we want to write it as 10 hours and 12 minutes. So there's an example of how you use a SIne rule to solve problems involving bearings. A lot of times with these questions, you'll use sine rule and cosine rule to solve these type of problems. So you'll combine those two rules, and you'll see the cosine rule in the next video.